class left? Well, circuits. I don't know about your other class. I don't think I have anything administrative to say. Do you have any administrative questions or other questions?
What is lab 14 and 15? Because they're not due on LMS. They don't have a due date.
Lab 14, I don't know anything.
Okay.
Lab 15, we're not doing it.
Yeah.
I mean, it's the last. I don't know why we're doing it on Wednesday. I don't think we've ever done that.
It's just on there. I don't know.
I think technically I'm not really supposed to accept written work after the last day of class.
Okay.
So signing something on the last day. No, usually I'll give usually homework 11, homework 10 was posted today, homework 11 is typically a kind of a comprehensive homework. And the due date there, I don't know.
No way.
Maybe Wednesday. Right. Any other questions? Moving forward? Okay. I guess first thing to address is I did a bad thing in last class. I mixed up my subscripts. So if you read the lab, things are correct, but my subscripts in the discussion were bad. So I lied to you in a bad way this time, not in a little white lie that was okay usually. So just to look at transformers again, and we're going to spend a chunk of today looking at transformers in general. To give you a little bit more background, what a transformer really is something, and actually this is not dissimilar to what they look like. You have an iron core, and then a winding. And then another winding. So when I talk about windings, it truly is windings around an iron core. This would be N1 windings and N2 windings. So that truly is physically what it is. Wire wrapped around some high permeability material. Iron, a fairly classic one. Has anybody been in the power lab? Show anybody in there? So you got some nice big transformers in there, heavier than the ones you saw in class yesterday. So one of the artifacts of transformers looking like this is they can weigh tens of pounds like the ones yesterday. And those are small transformers, or they can weigh hundreds of pounds. Hundreds and hundreds of pounds. And either side can be the primary, that's the two center. The handouts circulated somewhere. They make it to the back. No? Did they stall somewhere? They just sat by someone for a while? Okay. So, either side can be the primary or the secondary. One thing we saw in the lab. Is you can just turn the transformer around and make one side the primary and the other side the secondary. And again, just to remind yourselves, primary is the source side, and secondary is the load side, in a general sense. And we're looking at, again, from a circuit point of view, something along the lines of this. RS, transformer, and then RL. Or more generally, ZS and ZL. Or ZS and ZL are just impedances instead of resistances. So things we're familiar with. And in practice, as we start to look at power engineering concepts, we really are talking about impedances more than we are talking about resistances. Though, actually resistance is kind of the goal, but in practice, you have impedance. Inductance and capacitance exist. Anybody know why we would prefer to talk about resistance instead of inductance and capacitance? It's real. So you have real power in resistors, and you have imaginary power in inductors and capacitors. And we'll actually see that. And so this is typically defined 1 to n, where n can be any number 0 to infinity. So, in our write-up, just to remind ourselves, on the transformer, the ideal transformer relationships corresponding to current, and the voltage in the secondary and the primary. And we do have the relationship V2 equals NV1, and I2 equals I1 over N. And again, these are things we do on a box. I mean, and those are the correct subscriptions. And so that is something we do want to have in our notes at some point. And that's the ideal relationship. We apply voltage here, we get that voltage there. And did you see that? Well, you probably saw that fairly closely on the open circuit test. Was it reasonably close when you did that in the lab? But on the closed circuit test, well, the short circuit test, if we short this out, like we talked about in class last week, V2 shorted, V1 should be shorted. Was that true? Probably not as true. So what do we run into again in the situation? Real inductors have resistance. And so it's certainly diminished, but probably didn't go to 0. So going through all this, we have 2 approaches for circuit reduction. We can refer the secondary to the primary. And essentially what we're doing is, in words, we're replacing the inductor, or the transformer, and load with an equivalent impedance. That's our goal there. And so we take something along the lines of our transformer circuit, which is now scrolled off. We draw that. And that's ZS, being a little bit more general here. And that's ZL. We'll call that 1 to n. And so here's our original circuit, our source of course. Our equivalent circuit just looks like this. The source side still the same, no change there, as there would have to be for it to be equivalent. And then we have ZL equivalent, which in this case is ZL over n squared, which is where I messed up with my transcript, my subscript. So that is something to box up as well. And again, so this is referring the secondary to the primary, and here's our equivalent load. I'm going to sketch a box around that. And so what do we do now that we have it in this form? We do circuit divider, current calculation, whatever we want. It's a nice, simple circuit. 2 impedances and a source. Since they are impedances and since we are looking at AC values, still AC steady state, phasor analysis is still going to be with us, and we will use phasor analysis more. And so that's a tool that we'll use to find out. But there's not a lot of things to find out here. I mean, circuit reduction gets us this form and this form. Whatever's on the source side, if this is a more complicated circuit, like it is prone to be, well, we can use Thevenin equivalence, reduce it to some source, and some source impedance. And then on the load, there's all sorts of stuff on the load, your house, my house, your car, if you have an electric car, all that stuff is on the load. We lump it down to an equivalent impedance, and we get something that becomes this simple. And you can always do something this straightforward. Now that said, just to pose a question, VL equivalent equals VZL equivalent. So what is there? VZL, question mark. Is that true? Are they the same voltages? This tripped students up in the past, so it's worth thinking about for a moment. Is the voltage across this guy equal to the voltage across that guy? Well, there's one case it's true. When would that be true? N equals 1. So if it's a 1-to-1 transformer or isolation transformer that's 1-to-1, then that would be true. If N is not 1, is that true? So only if N equals 1, or in other words, N1 equals N2. So it's a 1-to-1 transformer, that's true. Otherwise, what's the voltage here? Well, we'll put a little knot in parentheses up there, except that VZL equivalent equals V1, and in this case, VZL equals V2. And that ideal transformer relationship has to hold. So in our analysis, V1 equals, put V2 there, N times V1, just so I can write it without fraction. So that has to hold in our circuit reduction. So this will hold, and of course, like we just said, they will be equal if the number of windings on each side is the same, N1 equals N2, or the winding ratio is 1. So in generally though, these two nodes go away, just like they did back in Unit 1 circuit reduction concepts. But these two nodes, we call that A, call that B. It's A, that's B, one of those perhaps ground. But those nodes have not vanished. They're still there. We've done circuit reduction. Everything to the right of those nodes has been lumped into whatever equivalent impedance we have, but those nodes have not gone away. On the other hand, we can refer the primary to the secondary. And so the same concept, we replace the load or source, replace the source impedance, and transformer. With an equivalent source and equivalent impedance, equivalent source impedance. And so, once again, just to redraw our circuit, there's the S, there's our transformer, our load, and so we're taking all this, I should have drawn my load out a little bit more. B source equivalent, Z source equivalent. And this actually looks very similar to the Thevenin equivalence, and it is. The derivation of the V source equivalent and the Z source equivalent does come out of Thevenin, and we looked at that a little bit in the last class, and so so this winds up being n squared ZS. And this is n times VS. And again, those are worth kind of boxing up. Those are relationships that hold when referring the primary to the secondary. Those will always be true. And once again, we can look and ask the question, is the voltage across here the same? Well, absolutely, it has to be. If they're equivalent circuits, well, ZL and ZL are the same in both circuits. Those nodes have to be the same. So if we're looking at load voltage, they are the same. Now there's another perhaps more important question that we've kind of ignored a little bit. Well, haven't touched it all in Unit 3, but we'll touch a lot in Unit 4. Between these equivalent circuits, I can go back and put up the other one as well. Between these equivalent circuits, if I calculate power here, so if I look at power load equivalent, a little Z in there, that PL, VL equivalent, PZL. I'll put that graph back up just a second. And we could ask the question as well, PVS equivalent equals PVS, referring primary to secondary. In two different situations. Considering this for a moment, this is power consumed, right? Bringing back a term we haven't talked about for a while. Power consumed. And this is power produced. And we can look at power produced in the referring the secondary to the primary, but that one's trivial somewhat. And here's our two circuits, or two equivalent circuits. There's a lot of stuff going on in the graph. Two fuzzy circuits. There we go. So you can tell. Well, you have the circuits in your notes, I hope. Here's our two equivalent circuits. Maybe are they on the screen? Sort of. Good enough. So if we ask this question, you looked at voltage, what about this? Are they equivalent? You want to hazard a guess? It has to be equivalent. So remember the voltage transforms as N, and the current transforms as 1 over N. But what's power? Voltage times current. So we have N times a 1 over N terms. And that vanishes to 1. And so in either case, our equivalent circuits, power can be calculated using either referral method. And that's an important thing we can do. And so ultimately we will want to calculate power. We'll touch on it near the end of today. But power is consistent in either case. We can calculate the power dissipated here and the power dissipated in the equivalent circuit, and they have to be the same. I mean, kind of observationally, how do we know that? Well, for them to be equivalent, the current going here has to be the same for both circuits. If this is equivalent to current in this loop, the current in that loop have to be the same. Otherwise, the voltage across ZS wouldn't be equivalent. So ZS is unchanged, whatever we look at ZS in the equivalent circuit. That'll give us the same contribution. If the current in this loop is the same as the current in this loop, what can we say about power produced? Well, power is V times I, and there's one source, so the same. So power produced has to be the same. Power consumed by ZS is the same. So the power consumed here and the power consumed there have to be the same. That's a little bit of a hand-waving argument. We can prove that mathematically, of course. But by observations, the power produced by this guy has to be consumed by these two guys. Or these two guys. But this and this are the same. So power produced there has to be the same. So there's something to make a note of there. It matters. So, and I think it was fairly straightforward in the lab, but just to revisit it for a second. We have a 5 ohm resistor. That's a transformer. Angle 0. So that's the source with 10 volts amplitude and 0 phase. Well, if we want to calculate the voltage across RL in this case, how do we do it? Well, we can refer the primary to the secondary. Using our rules. And so in that case, that's 1 to 10. We wind up then with an equivalent 100 angle 0 source. And 500 ohm resistor, 10 squared times 5. We'll be right up here, 10 times angle 10 angle 0 equals 100 angle 0. And then our R load. This is ZS equivalent, of course, and DS equivalent. And now it just becomes a straight up circuit divider, voltage divider. So VRL equals 500 over 500 plus 500 times 100 angle 0. So this 50 angle 0. 50 volt amplitude, step up transformer. Is that going to check with everything? Well, let's refer the secondary to the primary and just see if that works for consistency. I assume everybody was good with that. No surprises there. No questions? So, well, what do we wind up with? Well, we have 10 angle 0 here, so that guy's still the same. 5 angle 0 for 5 ohms. And now we have 500 over 10 squared equals 5. And that's our ZL equivalent. And so again, we have a nice little simple voltage divider, VRL equivalent, then 5 over 5 plus 10, 5 plus 5 times 10 equals 5 angle 0. Well, does that check? Does that check? Well, the voltage here, we just found out, that's V2, that's V1, and so this by definition is V2, right? I mean, that's connected to the secondary leads of our transformer. We define that as V2. And so the voltage across V2, they are in parallel. So we have 50 ohms, or 50 volts equals V2, angle 0. And on the V1 side, according to our referring secondary to the primary, we have V1 equals 5 volts. Okay. Well, are these two consistent? What has to be the relationship between V1 and V2? N. Does that check? Sure. In my world, 5 times 10 is 50. If you disagree, tough luck. We could do one more check here just to see if I lied to you a little bit. We could check power. So what's power? If we go back, we can use DC power concept, even though that is a lie. So we don't have DC power, but let's use power. For resistors, it's okay to do this. VRL squared over RL, that's an old power formula, right? We saw that a long time ago, physics 2 or something in the beginning of this class. And that winds up being 50 squared over 500. And 50 squared is 2,500 equals 5 watts. Did I do that right? You good? Break out your calculators. Well, let's check PRL equivalent. I contended that was going to give us the same power. And so we have VRL, lots of subscripts here, equivalent squared over RL equivalent. And so that's 5 squared over 5. And lo and behold, I did not lie to you, which is always good news. So we can check that with power as well. And so this method seems to give us a valid approach to solving something. Check, check. That said, what's the better choice? Do you want to refer the secondary to the primary or the primary to the secondary? Well, what does it depend on? What you're being asked. If you're finding the voltage across the load, what do you want to do? Refer the secondary to the primary, or primary to the secondary, sorry. If you're finding the source current, refer the secondary to the primary. It just kind of depends on where you're going. Now, as I said, inductance and capacitance exist. Well, in order to finish this problem, we need another piece of information that's a little bit neglected so far. These are impedance calculations at AC steady state. We need to know what? We need to know the frequency, exactly. And so what we'll look at in this case is the source, 10 volt amplitude, at 60 hertz. Why 60 hertz? That's a fairly meaningful number. That's line frequency. By line, I mean chargers or lamps or whatever. So that's a fairly important number to know. Actually, always surprises me a little bit. There's a few people that don't. So this is one of the key passwords to getting into the good electrical engineering parties. Don't forget that one. 60 hertz. And just for completeness, since we do talk about omega 2 pi, 60 hertz, that's around 377. And that's one that's probably worth just having handy. even memorizing. Not a huge fan of memorizing, but that's one worth remembering. 60 hertz in ratings, 377, fairly significant number. Now, if you go to Europe, I lied to you, they're not 60 hertz. I don't know where much of Asia is. Anybody know? Anybody from Asia know? Europe, I think, is 50. Someone said yes. So, 377 radians per second. What do we have to do now? This is now a phasor problem. Phasor analysis problem. We need to convert this 10 angle 0. That's still 10 ohms. And by chance, this winds up being 20. Negative. And if we're trying to find IL, well, what do we want to do? What's the choice here? Well, if we want to find IL, I personally feel it's easier to refer the primary to the secondary. If I'm going to refer the primary to the secondary, equivalently, let's give ourselves some blinding. 1 and 5. So we should somewhat agree that's 50 ohms or 50 volts. So anybody have any problems with that? Now we have a resistor and a capacitor. Is that going to change the referring on the source? N times Vs still holds. So I drew that previously as some Vs. Well, Zs is anything. It's a complex impedance. It can include a real part and an imaginary part. So what does that mean we can do with our resistor and a capacitor? Well, we can transform those directly. And so that just winds up being 250 minus J 500. 5 squared times 10 and 5 squared times minus J 20. Do that directly. Is that becoming popular, using the old phone ring thing? I guess the students coming in now may have never actually heard a phone ring. Not without a ringtone. Class of whatever. That's 2019. I was surprised when a friend's nephew told me he had never played a turntable before. He didn't know how to turn it on. You never used the turntable? What's that? So all of you use the turntable?
No.
Wow. I'm a little bit surprised. Anyway, so back to circuits. A lot of important circuits actually in early music. Still a lot of important circuits. It's gotten a lot more complex. It's gone from, actually this class in the early days of playing music, this class would have done you well. You would have been able to build filters, amplifiers, and all that stuff. But now it's all done visually, so you have to wait till your visual electronics class your senior year to build your own stereos. So if you want to build analog stereos, you can use everything used in this class.
I know a person who has.
What's that?
I know a person who has that one. So has its own like analog stereo and so
You still need to use transistors. So anybody really into music? Like spend money on expensive equipment? Do you use vacuum tubes?
I don't use vacuum tubes.
Can you hear the difference with vacuum tubes?
I can hear distortion with vacuum tubes.
Actually, they say vacuum tubes are better. That humans like vacuum tubes.
If you're getting some really expensive tube equipment, you can get better vacuum tubes, but on the cheaper end of things, they're pretty distortion heavy.
Huh. Okay. I don't have a good enough ear for it. That's interesting. So, here we are. How do we find IL? Well, this is now just a series circuit problem. Essentially, we can do circuit reduction. One more time, angle 0. And what do we wind up with? You can draw that as a black box. 500 times square root of 2, angle minus 45. I did that fairly quickly. Does everyone agree with that? That's got to be the same circuit. That's the current through RL, or 250 ohms, but in the equivalent circuit, and it's referring the primary to the secondary, the current through here, all the same. So these are equivalent components. And now we can very quickly find IRL, 50 angle 0, over 500, square root of 2, angle minus 45, and that's 1 over 10 square root of 2, which is some number, angle 45. And we can go back and convert that to a real value, real expression, cosine 377t plus 45 degrees. That's something you have to do in the exam, and it's something we'll have to do in the Unit 4 as well. So, we can do all this with complex complex impedances, as we must. Let's consider a slightly more complicated case. Is this a reasonable thing to do? Just to kind of look at this, can we have 2 transformers in our circuit? Sure, no problem. That's a reasonable thing to do. In terms of this circuit, what type of transformer is this? Just to pay attention. It's a step up. And what's this? Step down. And so in this case, n equals 5. In this case, n equals 1/2. So if it's a step-up transformer, n greater than 1, we saw that last class. If it's a step-down transformer, n is a fraction less than 1, but still positive. So nothing less than 0. So step-down transformer and a step-up transformer. How do we find VRL? Well, where are you going to start? We're trying to find the voltage across the load resistor. In that case, which way do we want to go? It's the same question we asked before. We want to refer the primary to the secondary. Well, thinking about that for a moment, if we look at this middle section, just having the source here, the load there, what can we say about this middle section? Is it a primary or a secondary? Well, it depends which way you're going. So, if we're going this way, we merge this guy into this guy, well, this is the secondary of this load. This is the primary side. But it's the primary of our secondary transformer. So we have to be careful when we ask which way we're going. So it's not necessarily as clear. It depends on the transformer you're talking about. This section here This is secondary for this transformer and the primary for that transformer. Not an integral thing to worry about, but something to be aware of. And so, well, how are we going to do this? Part by part. So I personally would start with the primary. This is our primary, and then refer that to that secondary. We'll leave the voltage there. So 10. We don't have any impedance, frequency dependent terms, no capacitors, no inductors, but we could say it's 60 hertz just for fun. If we have a purely resistive circuit, frequency arguably doesn't matter. Though again, that's a bit of a lie, as you saw yesterday in the lab, and we'll look at that case as well. Frequency does matter. So what do we wind up with? 50, 100, 100, 100, and there's our transformer, our second transformer. Well, now the question becomes, what do we want to do next? We have some choices. We have this slightly more complicated circuit. We have all these resistors. What could we do? Yeah, be specific though.
Maybe simplify the circuit down to 150 ohms, like combining all three resistors.
Yeah, but what's that called? What was that? We want to do Thevenin. So we want to do Thevenin analysis. Our goal again is to get something along the lines of just whatever it is, a single source impedance and a single load impedance. That's always our goal. Why? Because I don't like to count higher than 2 components in a source. If I have just 2 components in a source, my life is easy. And I like it when my life is easy. So circuit reduction, in this case Thevenin analysis, is a good choice. Now arguably, could I still refer the primary to the secondary here? Is that going to be equivalent? Sure. I could refer all this, move it over, without doing circuit reduction, but I'm a little bit more likely to make a mistake myself. So I would do the Thevenin reduction on this because I can just see it fairly easily. There's the load, and so we should recognize the Thevenin in this case is 25 angle 0, angle 0 in there. Everybody agree with that? We've done this problem a lot, so you should agree that's 25 angle 0. And we should get, in this case, there's no Z, we just write it as R Thevenin, 150 ohms. So I did that without writing the circuits out, which always a bad thing. It's always good to draw the circuits, but hopefully we can kind of see this now. Everybody agree with both those numbers? And so now we're left with a nice simple circuit, one that's more familiar for us, which is always a good thing to have. 25 angle 0. There's our transformer. There's our load. And that's 2 to 1. And now we can apply the transformer characteristics that we've derived without much worry about writing things down incorrectly. This is 2 to 1. So our N equals 1/2. And so when we do the referring primary to secondary, we need to use that 1/2. And so 1/2 of 25 angle 0 equals 12.5 angle 0. And 1/2 squared times 150 equals 37.5, and then on the road. And again, it's important to remember our step-down transformer has an N, a winding ratio that's less than 1, a fraction less than 1. And so we can now find VRL, quite straightforward. It's 1/3 of 12.5 angle 0. So 12.5 over 3, angle 0. Everybody agree with that? Again, I'm not writing this, so you get all out. If something troubles you, make sure you have it. Anybody still writing? Let me throw one more at you before we do a team assignment. And then you're waiting usually for it. Now here we have to be careful of a couple of things. Kind of first off, how would we analyze this? Everybody hear that? Everybody in the back, how would you analyze this? How would you analyze it in the back? All of you hiding back there, hoping that I don't call on anybody. So. How would you analyze this? Someone said it. Go ahead. Read it loud. Use superposition. How did you analyze it on the exam? Superposition with your friend. So use superposition. Now there's another thing that we haven't talked about yet. A number of you did this in the lab. What happens if you reverse the probes when you measure AC signals? So what happens? You get the negative. You get a 180-degree phase shift. Well, what happens if I take H1 and H4 and reverse those leads while leaving X1 and X3 the same in the lab? You get a phase shift. There is a convention. And it matters when we have multiple sources. Well, it matters in general, but matters more multiple sources when we're considering superposition. To go back, we have V1 here, V2 here, I1 and I2. There's something called the dot convention. And that's our dot convention. It's the orientation or the connections of the leads for the two transformers. In this case, you can say they're connected in parallel. On the other hand, we could have something like this. In this case, our two transformers are connected in anti-parallel. So we've only been really looking at the top one, but what happens if we connect things backwards, so to speak? Well, we wind up with a 180-degree phase shift. That's all this means. it matters, and you saw that. When we're looking at amplitude, and that's what we looked at in the lab, I mean, we can kind of ignore the phase shifts in that case. But in general, that's not a good idea. A lot of times phase matters in circuits, and circuits are totally dependent on phase. And so we do need to be careful of how we hook things up. We've been a little bit negligent of that. But in this case, again, I'm just going to use this type of winding. Well, as I consider this, if I'm trying to find I2, the current here, what am I going to do? I'm going to use superposition. What's superposition going to look like? Well, here's the left source. One and two. And then effectively for this source, I have 100 ohm load. And then here's our other source. What's that? We are talking about voltage sources, so I shorted them out. How do you turn a voltage source off? You short it out. How do you turn the current source off? You open it. And this is still 1 to 2. Well, what's the equivalent circuit? In this case, I want to find the current in this loop, right? Here's I2 due to V1. There's a 2 there. And then here's I2 due to V2. Different contributions from each source. And we're going to add them. That's what superposition was. We add them. How am I going to find this guy? Well, I'm looking for the current in this loop. So in this case, I probably want to refer the secondary to the primary. And this is a step-up transformer, n equals 2. And so we get something along the lines, refer secondary to primary. Tan angle 0. That's 50, and that winds up being 25. And now for this guy, and we could finish this out, I suppose. That winds up giving I2 to the V1 equals tan angle 0 over 75 ohms. Two resistors in series. There's our contribution, 10 over 75, angle 0. Now we do need to be a little bit careful here on this side. We have, again, a dot convention like this. So they wind up parallel. But if this is positive and this is negative at t equals 0, which would be what the phase 0 here meant, which way is current going to flow? It's going to flow up, which means current's going to go here by our dot convention. Which way is current going to flow on the left loop? Well, saying things in terms of clockwise and counterclockwise, current's going to flow on the right loop in the counterclockwise direction. By our dot convention, current is going to flow counterclockwise in the left loop as well. So that's probably the way of thinking about things in our dot convention. The direction of current in the associated loops is consistent. If we close this with some sort of circuit, close that with some sort of circuit, we see I1 going like this, I2 going like that. If we reverse the direction of I1, we also reverse the direction of I2. Though, just to emphasize, these are AC signals, they're oscillating back and forth. What that does for us, this gives us a reference for the phase. So that's really all we're asking for, is what is the phase. In this case, the phase between the contributions of these two is 180 degrees out of phase. So at t equals 0, this guy's flowing clockwise. At t equals 0, this guy's flowing counterclockwise, which is a 180 degree phase shift. But rather than including that in the phase term, we can just write that as negative. Effectively, 180 degrees is just a negative sign. And you could always write something v naught cosine omega t plus 180 equals minus v naught cosine omega t. Trigonometry. It does get a little bit tricky to make sure you pay attention to that stuff. But in this case now we need to do what? We're going to refer the primary to the secondary. Does it matter that the primary is on the right side? No. By convention, I usually draw the source on the left. That's a convention. Doesn't matter. In most books, you'll probably find the same thing. We've done that so often. We always have our source in the lower left, but that's a meaningless thing. So here's our primary. We're going from right to left, so to speak. Well, as far as the primary is concerned here, what type of transformer is that? Step up or step down? You have to pay attention to what direction you're going. So if we're going right to left in this case, then that is a step down transformer. And so what do we wind up with? That winds up being 50. No change there, of course. This is a step down. That's 25. And that's 7.5. Angle 0. And at t equals 0, current's going that direction. And so that's going to give us I2, I don't know why I call that I2, but do the V2 equals minus 7.5 over 75, angle 0. And we can add those up. Does everybody agree with that? So superposition is your friend. What would I do if I had complex impedances here? What would I do if I had complex impedances there? Same thing. Which is good, because that's what your team is underneath.
Adjust that, please.
Yeah.
And so, in some sense, we have that winding. If we take coils in air, the coil here, drive a current through here, I1, you don't have to write this down, this produces a magnetic field. And you would have maybe seen this in elementary school or something like that. Did anybody wind a coil around the nail and then go around and pick up paper clips? If you didn't, go home and do it today. So you made an electromagnet. So that's what's going on here. Magnetic fields, and the magnetic fields radiate through the space, and actually some of the magnetic fields go through this coil. And what happens if magnetic field goes through this coil? Well, there's something called Faraday's law. And what does Faraday's law do? Well, the magnetic field is going through this coil, and the magnetic field is oscillating because this current is oscillating. In other words, it's AC. So we have a changing magnetic field, and that excites a current in this guy. And so that's how transformers work. You have a magnetic field excited by a primary that induces a current in the secondary. So we talk about voltage and whatnot, but really this is more magnetic field and current concepts of magnetics in terms of the electromagnetic side of things. There's also Lenz's law, which is involved. All sorts of guys worked on this. So, well, if we think about this from a real physical sense, if I take two coils and I wrap them up right on top of each other, what can we say about the coupling of the magnetic field? It's pretty good. I mean, you have one coil, you wind it, and then you take another winding and put it right on top. The magnetic field decided in the one coil is pretty much in the second coil, and that's what solenoids are if you've heard of solenoids. On the other hand, what happens if we move these further apart? What can you say about the coupling? It gets lower. As you move further away from something, the magnetic field is weaker, and so the coupling is further or weaker as I get further away, and the excited current will be lower, and likewise the excited voltage will be lower. And actually this is something that's being investigated maybe over the last 10 years or so in terms of wireless power delivery. Has anybody heard of this? Yeah. Actually, Connor and a couple other people at RPI have been working on this. And the idea is you have, you know, a loop somewhere in the corner of your room, and that's plugged into the wall, radiating power. And then your wireless power receivers have resonant loops that resonate with that loop. And you have a strong magnetic field coupling between the two, and then you could have the cordless room. There is a huge problem with this idea. Does anybody know what it is? It's low efficiency. You waste a tremendous amount of power. I mean, even when these things are good, and I've heard people say up to 80%, I think, yeah, maybe if you're standing on your head with your fingers crossed and whatever, but 50% probably a little bit more reasonable, and even lower as things get moved around the room. The geometry has to be perfect. It's pretty cool, I won't argue with this. But in terms of, you know, let's go green and save the world, well, this is not a good choice. Other than you don't have any wires around the room, so you're less likely to trip and see something. But as far as we're concerned, we have these transformers. We've done this referral to primary, referral to secondary. Effectively, I told you these are inductors. So to draw this again, this is an L1, this is an L2, and we can define the coupling using K, which is a coupling coefficient. And essentially what we have is mutual inductance. Current in L1 excites a current in L2. That's what transformers are, and vice versa. And so everything we've done so far has been using self-inductance. So the inductance of a single coil and its own impedance with regard to the current in relationship to voltage. Now this is mutual inductance. Whatever we do here produces a response here. And so there's a term, mutual inductance, M. And that's in Henry's as well. So it is like an inductor. So mutual inductance M, and M has a definition. If we look at two inductors, M is defined as K times the square root L1 times L2. And that's worth remembering. You know, I suppose it's boxable. K, this coupling coefficient, is some value between 0 and 1, less than or equal to 0. With K equal to 0 being no coupling at all.
It's all blurry. There we go.
No coupling, i.e. current in L1 No excitation in L2. K equals 1, maximum coupling. And from a field point of view, that would mean there's no leakage field, which is something power engineers worry about. I.e., current in L1 produces the maximum excitation in L2. And so there's our limits. Transformers, ideal transformers, K equals 1. That's the goal. Infinitely permeable transformers. Well, K equals 1 for an ideal transformer. What would you estimate for a good transformer? Actually, pretty darn high, 0.99. So our transformers, lab transformers, are probably pretty good. I would guess they're around 0.97 to 99, somewhere in there. Pretty good transformers. Partly that's not just the materials, but the geometry and the way they're laid out as well. There's a lot more stuff going on here, a lot more aspects with regard to fields that gets very, very interesting, and that's why they're graduate classes. For us, we're just going to look at this one expression, relate it to this mutual inductance, K equals square root of L1 times L2. I'll give you K. Anybody have any idea how you would actually find K in practice? It's a little bit more complicated than that. You perform, well, if you're going to do it from a simulation point of view, you perform fairly expensive computational electromagnetics, which in the past could take a couple of days, but now is much, much faster. And that's just to do one case. So K depends on the geometry of the inductors, the materials of the inductors. It's a very non-trivial thing to calculate. L1 and L2 actually are reasonably easy to calculate. We have the bridge circuits, we can estimate L1 and L2. But the coupling between them, trying to figure out how they're coupled, kind of hard. And again, secondary effects really make this complicated. Now, what does that mean for us? Well, the goal here is to get an equivalent circuit model without having to do any of this referring. So, a mutual inductance circuit, well, if we think about a little bit more complicated scenario, there's some load, some ZS, some V1, call that ZS1, and there's our inductor with its coils and all that not. And then similar to what you just did, here's another source, ZS2, and the V2. And so we have a current or a voltage across this guy. And it's the contribution, call that VL1. Well, VL1 equals, we should recognize, it's been a while, but LDI-L1 by dt. So that's the relationship between voltage and current in an inductor. We haven't done that for a few weeks. Bring that back. And that's just this circuit by itself. And we can go through and do whatever transient or AC analysis we want to actually figure out what that is. But I said these are coupled by mutual inductance, so if we drive a source here and current through L2, that also excites a voltage in L1. And so there's a coupling term by this mutual inductance. There's a 1 there. DIL2 by dt. So the voltage across L1 is due to two contributions. Its own inductance, and then the coupling via the mutual inductance of the other source. And likewise, we can say VL2, and leaving off my subscripts, is L2 DIL2 by dt plus M DIL1 by dt. And so those are the excitations on both sides. There's VL2. Well, what can we do here? Well, the equivalent circuit model, taking this into consideration, this is a fairly simplistic approach, but something we can do as a first order. We can call it the T model of mutual inductance. And appropriately named, it is like a T. Here's the coupling between the two inductors. Here's VL1 across those inductors, and there's VL2 across that inductor. What are the components here? Well, the equivalent model is, that's the mutual inductance M. This is L1 minus M, and that's L2 minus M. And essentially, what we're doing is we're replacing this with the T model. And so if we know L1, if we know L2, and we know K, which gives us M, just by using that M equals K times earlier L1, L2, then we can redraw this circuit. And so, in some sense, we can take this, drop that right in there, and do all our circuit analysis, superposition, find current through ZS1, ZS2, etc. Don't have a lot of time now. I think I'd rather push off the next concept because it's going to take me a few minutes.